Welcome back to lesson 4. In this video, we're going to talk about statistical significance and also how to read regression outputs. In lesson 1 and 2, we read regression outputs, but it was very little information, and this is going to be much more than that. In this video, we are much more interested in accepting our alternate hypothesis and rejecting the null hypothesis. All that you want to do is have some confidence in accepting that something is happening in the real world and having the data to back it. So stay tuned and then let's go through the lesson. And also don't forget to like and subscribe. It really means a lot. See you in the lesson. Remember, in our first lesson, we formulated a hypothesis. Within the scientific community, before we accept some research findings as truthful, it needs to pass this test of statistical significance, right? Remember, during the COVID-19 period, most of the vaccines that came up with this sort of confidence interval, and they were saying this vaccine has 95% confidence interval that is effective and things like that. The same thing has to do with research findings. We want to know that there is enough evidence to accept some scientific findings. In this video, we're going to stick to the same World Development Indicators data set. Our independent or explanatory variable is still gross domestic product per capita, and our dependent or outcome variable is still health spending. But the hypothesis that we formulated in lesson 1, that countries with higher GDP will spend more on healthcare, has changed a bit. So we have divided this hypothesis into a null and alternate hypothesis, and this is typically how the research process usually is. Now, our null hypothesis is this intuition that there is no significant effect of the independent variable on the outcome variable. In other words, everything that we are observing as happening between GDP per capita and health spending of countries is actually just happening by chance. Don't think that it's something that we should accept as a relationship that is occurring constantly, right? And then we have an alternate hypothesis. And our alternate hypothesis is that there is indeed a statistically significant relationship between the independent variable and the dependent variable. In other words, our alternate hypothesis is saying that something is actually going on here, and what is going on is that as GDP per capita of a country increases, health spending is also going to increase. So the null hypothesis is contrary to the alternate hypothesis. The null hypothesis is saying stop this, nothing is going on here, and the alternate hypothesis is saying something is actually going on here. As a researcher, mostly we would want to find some support for the alternate hypothesis, but this isn't always the case. In research, we don't go in looking for evidence that we want. Sometimes mainly the goal of research is to find out what actually exists. So whether it's our null hypothesis or alternate hypothesis, we have to accept it in good faith. So before we can accept our alternate hypothesis, or before we can reject our null hypothesis, we should have some grounds to do that. And this is the concept of p-value, right? Now the p-value, the p here simply stands for probability. It talks about the probability that the observed correlation between the independent and dependent variable is as a result of randomness or is happening by chance. So whatever thing that is happening between GDP per capita and health expenditure, we want to find out that what is the probability that this is happening by chance, right? So the smaller the p-value, the better for us, because the smaller the p-value, the smaller the evidence that this is happening by chance, and therefore if it is a small probability that is happening by chance, then there's a big probability that what we are expecting is actually real, right? So we want a smaller p-value. And the p-value is always linked to our correlation coefficient or the estimate. So whatever estimate that we observe as the relationship between our x and y, the p-value is telling us the probability that what we are observing is only happening by chance. And we want a smaller p-value in that case. So this is also tied in with confidence interval. With a smaller p-value, for example, if you have a p-value less than 5%, it means that there's 95% confidence interval. In other words, if there's less than 5% probability that this is happening as a result of randomness, then there's about 95% confidence that we have in what we are seeing in our regression output, for instance, or what we are seeing as the relationship between x and y. So the scientific community has established a set of p-values that they think that is enough to establish statistical significance. Some journals or in some fields, the p-value required is much more smaller than others. Let's go through them quickly. So the first threshold for a p-value is a p-value less than 0.05. So this is usually the threshold for establishing statistical significance. And this p-value is telling us that if if our p-value, if what we want as a p-value is p less than 0.05 and we get it, what it's trying to tell us is that our there's a less than 5% probability that what we are observing between x and y is as a result of randomness or chance. So if there's less than 5% probability and 5% is our threshold, then that means that we can accord statistical significance to our correlation coefficient. In other words, we can we can fail to reject our alternate hypothesis. So we would accept our alternate hypothesis and then we will reject the null hypothesis that whatever is going on here is not real, right? It's happening as a result of randomness. In other fields, the p-value is quite stringent. So in other fields, there's a p-value less than 1%, which is p-value less than 0.01, right? So in this case, before you accept your alternate hypothesis, right, or before you reject your null hypothesis, then you should have a p-value telling us that what we're observing as a result of randomness is so small that it's not even up to 1%. In other words, we have a 99% confidence interval that whatever we're observing is actually real. So there's another threshold of a p-value which is p less than 0.001, and that is the most stringent p-value, right? It's sort of like 99.9% confidence interval to accept your alternate hypothesis. So this p-value is saying that there is less than 0.1% chance that this is as a result of randomness, or there's 0.1% probability that what we are observing is actually not real. And that gives you a 99% confidence interval that what we are observing is real, right? So we can accept our alternate hypothesis. So what we are going to, and we are going to go to our R studio and check out how this reflects in our regression output, and simultaneously we can learn how to interpret the regression table in a more basic form. But what you would observe is that the highest form of p-value is denoted by 3 stars. So the third threshold here is going to be denoted by 3 stars. The second one is denoted by 2 stars, and then the first one is denoted by just 1 star. So the more stars shows more statistical significance. So let's go to our studio and generate a more detailed regression output for what we observed in lesson 1 and interpret it using what we've just learned. So in lesson 1, this is what we did. We analyzed the relationship between GDP per capita and health expenditure. In other words, we want to find out if increases in GDP per capita increases countries spending on health. So I'm going to run everything we did in lesson 1 up to line 41. So the last thing we did in that lesson was to execute a code to model out our linear regression, right? And we stored it in an object called lm test. So if you call lm test, you should see some regression output. But we want more than this. Typically, if you want a regression table that you can import to your research paper, you need more than this. So let's use a function called summary in R to generate our regression output. Remember, we stored everything in lm test, so we call lm test inside summary, and then we run the code. And what we have here is a more detailed regression output for the regression analysis we did. Let's go through our regression output real quick. So we have here our summary statistics: mean, first quartile, third quartile, our medium, and max. And then we have our coefficient. So again, just like we saw in the previous lesson, the coefficient here is really is quite funny. So what we see here is trying to tell us that with a unit increase in GDP per capita, the health expenditure of countries is going to increase by 0.00007 units, right? Now this minus 0.05 you see here, it just tells you that you have 5 zeros in front of the 7. So it's a really small increase in health expenditure with increases in GDP per capita. But there's more to this model, right? We've not added other covariates, so that is not the main reason why I'm doing this lesson. But the main thing you should pay attention to, as far as this lesson is concerned, is these stars here that show statistical significance. We can see that these results are highly statistically significant at a p-value of 0.001, or in other words, with a confidence interval of 99%, right? So that is how you interpret this. If you're writing a paper on this, you would interpret this as a unit increase in GDP per capita leading to 0.0007 unit increase in health expenditure, and then this result is highly statistically significant. But one thing that points, like, there's obviously something wrong with this relationship, right, or this model, because if you look at our R squared, now how you interpret this R squared is very, very, very important. The R squared is simply telling us that how much of the actual relationship between GDP per capita and health expenditure is explained by this model. And we have an R squared of 0.29% or 0.29, which is like 29%. So what is telling us here is that this model only explains about 30% of the relationship between GDP per capita and health expenditure, right? Which is not really much. It's not something that we can hold on to. So even though our results are highly statistically significant, we cannot accept this analysis because our R squared is so small. The adjusted R squared adjust R squared based on the number of predictors. So sometimes some people might conduct multivariate analysis, which we are going to get to very soon, and include so many predictors or so many independent variables that makes the model clumsy. And R squared adjusts for all these things to make sure that we have a higher explanatory power, and unnecessary predictors or unnecessary independent variables are sort of muted, right? So our adjusted R squared here is 0.28, and it's also telling us that our model only explains about 29% of variations in our outcome variable. So your R squared are always important before you jump to, you know, conclusions and say, well, I found statistically significant results that helps me accept my alternate hypothesis. You should pay attention to your R squared because it really tells you whether your model has some statistical power or not. All right. So this is all that statistical significance about. It's sort of the basics to help you understand it, and that is how you sort of make sense out of it from a regression output in R. I hope this lesson benefited you, and if it did, please like and subscribe. Really appreciate that a lot. And send comments. Let me know what I'm doing better, what I should improve on, and yeah, I'll be glad. So hope to hear from you in the comment section. Yeah. Bye and see you in the next lesson.